This is the LI-6800 portable photosynthesis system. It's an instrument normally used to measure leaf level physiology, things like carbon assimilation, stomatal conductance, chlorophyll A fluorescence at the leaf level. It's comprised of a console that handles the user interface, data logging, and air conditioning, and a sensor head where the measurements happen. Traditionally, this instrument was only meant for measurements on leaves or small plant canopies. We now offer the 6800-18 aquatic chamber, this piece here, that allows us to adapt the normal instrument to make measurements on samples in liquid suspensions, so like algal cells in a growth medium. The aquatic chamber and the 6800 are a bit different than the instruments that are normally used to measure algal physiology, in that here we're measuring carbon dioxide and as opposed to oxygen, and typical oxygen measurements are made using what we would call a closed transient approach, where you're looking at the change in concentration over some period of time. In the 6800, we use an open flow through steady state approach to make our carbon flux measurements or to compute carbon assimilation. We have a liquid sample that sets here. In the bottom of this sample holder, there are some tiny precision machined holes that we send a very precisely controlled airflow through. That gives us very uniform and controlled bubbling through the sample. That uniform and controlled bubbling ensures that we have a constant and very high mass transfer coefficient between the air that we're sending through the liquid sample and the liquid sample itself. That ensures that the sample is at equilibrium with whatever carbon dioxide concentration it's being provided. That carbon dioxide concentration is under instrument control. The instrument brings ambient air in between these two chemical columns. It sends that air through this first column that contains soda lime that strips all the carbon dioxide out of it. And then it has a small cartridge of compressed carbon dioxide and a mass flow controller that's used to add carbon dioxide back to some user set point. That air goes to the sensor head, where it gets measured by a pair of infrared gas analyzers. One of those gas analyzers is measuring the carbon dioxide and water vapor concentration of that air before it interacts with the liquid sample. And the other one is measuring the carbon dioxide and water vapor concentration after it interacts with the liquid sample. And we compute the carbon assimilation rate based on the difference in concentration between those two analyzers and the flow rate through the sample. This is different than the traditional oxygen measurements in that doing the measurement this way, both carbon dioxide and oxygen are constant over the period that we're making the measurement. So today we're going to take this instrument into the lab and we're going to use it to measure photosynthesis irradiance response on some Chlorella vulgaris that I've got growing in there. And we'll look at the data afterwards. So we're going to pull some cells from a culture that I've had growing for a couple of days. These cells are going to go into the centrifuge and we're going to spin them down to separate them from the growth media that they're currently in. I'm going to resuspend them in some growth media that I set up this morning to bubble with 400 ppm tank air so that it's pre-equilibrated at my measurement conditions. I'm going to resuspend them to 15 milliliters because that's our working volume in the chamber. And I'm going to add a small aliquot. In this case, it's equivalent to 0.5 grams of carbonic anhydrase. And that will help ensure that the carbonate system remains in equilibrium as we make these measurements. Carbonic anhydrase helps with the hydration of carbon dioxide and the interconversion between bicarbonate and carbon dioxide in solution. These cells are going to go in the chamber. We're going to start them in the dark. And we're going to slowly increase the light intensity and make measurements of chlorophyll fluorescence, particularly phi-PS2 and electron transport rate, and carbon assimilation as we move across light intensities. On the instrument, I've already set up an environment where I'm controlling the air entering the sample at 400 ppm, the same as what I equilibrated my media to. And we're going to open a log file And then we're going to use a pre-built script on the instrument to do the photosynthesis irradiance curve under instrument automation. So I'm going to hit start here. We'll come back and look at data at the end. Now that the curve is finished, we're going to remove the cells from the chamber. I'm going to save some of these so that I can calculate a cell density for this measurement. We'll just pull them out with the syringe, and then I have a bottle of deionized water here that we're going to use to triple rinse the chamber, and that'll get any residual sample material out. Here's the data the instrument collected during the photosynthesis irradiance response measurement. I'm showing carbon assimilation here, solid symbols, increasing as the light intensity increases. And I'm showing phi PS2, the open symbols. This is the quantum efficiency of PS2, likewise decreasing as the light intensity increases. Here are the same carbon assimilation numbers, but now plotted against the relative electron transport rate. I like to show this because when we measure carbon dioxide and ETR, we generally expect to see a near perfectly linear relationship with changing light intensity, even at the highest light intensities. That was an example of how the aquatic chamber works and how it can be used to measure photosynthetic response to light at constant oxygen, in this case ambient oxygen, and constant CO2, in this case a nominal ambient value. If you'd like to see more example data, we have a white paper available that shows the instrument being used to measure photosynthetic response to light at different oxygen concentrations to look at the impacts of photorespiration, and shows an example of the instrument being used to measure the photosynthetic response to changing carbon dioxide in solution.